Next speaker will be Dr. Robert Clarisó, and the title of the paper he will be presenting is On the Verification of UML OCL Class Diagrams Using Constraint Programming.
Well, this is joint work with Jordi Cabot, the iCrea researcher that is going to join UOC soon, and Daniel Riera, both from IT Multimedia and Telecommunication Studies. And well, the talk will be structured in this way. Now we're going to talk about quality assurance in software development. We will start by talking about what is the use that is made in models in the software design and development process. Later on, we'll move specifically about the quality assurance problem in software development. And finally, we'll talk about what is the specific solution that we have proposed, which is based on a paradigm called constraint programming. So first of all, we're going to talk about software, and more precisely about the software design process. So typically, software is not implemented directly. You do not start by producing code in the first day. First, you have to start thinking about what is the functionalities of the system that you want to develop. And in order to achieve that, you start by producing models of this software. What is a model? I wanted to explain it with something useful and important like cats. Everybody says that the internet was invented to exchange pictures of cats. So this is a very important topic. And if you want to explain to someone what is a cat, you will probably use a depiction like this one. On the left, that would provide a good image of what is a cat, but however, if you want to do something different, like provide a computer animation of a cat, you will need a different model, something that takes into account the different components of a cat's body. So precisely that is a model. It's a description of a system that takes into account different features depending on the goal that you want to achieve. And the beauty and the power of models is in the abstraction capacity, because a model only includes the relevant information that is needed for that purpose. This means that it can be very simple, and also that it can be reduced, so that if later on you want to talk about tigers instead of cats, maybe you can reuse the same type of model. So in a software system, you might be interested in describing different features of a software system. Like, for example, the one that comes to your mind is the behavior. What is the sequence of events, a sequence of activities that a software system performs? And there are modeling notations that let you do that, like activity diagrams. You might want to describe the information base. So what are the pieces of information that appear in the system? Whether we have students, we have grades, we have courses. And also, what are the integrity constraints that appear in this system? Like, for example, each course has a unique code. You might also want to describe what are the different features that relate different families of a software system. Like, for example, if you have the free version and you have the professional version, which is paid, and they have different versions, you might want to explain what are the relationships among them. Okay, this is done with type of models called feature models. We are going to focus on the models on the left, what is called UML class diagrams, which describe the information base. What is the information that is being used on a software system? And before moving on how to analyze them, we'd like to discuss why are we using, or what are we using these models for? The first thing that we might want to use these models is for explaining how the system works. For example, if you have a very complex legacy system in a company, you might want to explain how it works so that new employees understand how it operates. It's something called reverse engineering, and typically is done by extracting models from the code base of an old system. You might also want to use the model to check whether your initial idea about how the system should work actually works in practice. So, for example, to simulate whether the system operates as expected. Something else that you might want to do, which is more practically oriented, is, well, once you have the model, you might want to get the final implementation of the software system directly by pressing a button and generating the final code of the system. So these might be some of the goals that you may have in mind when analyzing a model, and we're going to focus on verification and validation. And when we are doing that, well, I think I don't need to explain you how important software quality is. It might be something as funny as finding a Windows error, a blue screen of death in a software system. This is not probably a life-threatening error, but in aerospace, energy, or medical scenarios, software systems may be safety critical. So failures in software may cost a lot of money or may cost lives. So it's very important to make sure that software systems are correct. And what do we mean by correct in the sense of a software system? We might be asking two different types of questions. The first one must be, is the model right? Are we building a correct model in the sense that it's well-formed, it does not have syntactic errors, for example, that it is inconsistent, that there are no contradictions. For example, this is a very simple model, this one, and it has one of the typical rookie errors when modeling. It says, you can think of it as saying that a person needs two parents. This might be a very simple integrity constraint, but you think of it, then if one person needs two parents, then their parents need two parents as well. And you end up needing an infinite number of persons in order to use this software system. So this might be a typical mistake. Or another mistake that you may have is that you may include information that is redundant, is not needed. And this is typically a source in which later on you will find some problems. Another type of problems, of questions that you might want to ask about the software system is whether the model that you have defined is the right one. Not if it is correct, but if actually what the user of the software expects. For example, going back to cats, you typically want to model on the information about the system. So for example, a cat has 4 legs, not 2. Also, the model has to be precise. It has to describe reality. So cats have no arm going out of their backs. And also it has to be citable, because typically when you build a software system, you don't want that in the end the client says, no, I did not want a cat, I wanted a tiger. It's something that you would not like to discover at the very last minute. So the questions on the right, they are very hard to analyze automatically by a computer. But on the other hand, the questions on the left, they are feasible to be analyzed by a computer. And how it is done? It is done using a computer tool called the formal verification tool, which is given the model that is going to be analyzed, and also the correctness property that needs to be checked. Okay? And this tool internally transforms this model into a formal notation and give this notation to a theorem prover or a constraint solver that analyzes this model and provides some feedback. The feedback might be as simple as saying, yes, the property holds or it does not hold, or it might provide more advanced information, such as a proof certificate stating why the model is correct or not, on an example or counterexample where the model exhibits its behavior. So this problem is computationally very complex, and it's not possible to get it right in each and every dimension. So when you are implementing a formal verification tool, you need to establish several trade-offs. So for example, the tool that you're using might not be automated. It may require user assistance to complete the proofs, or it might not be efficient enough. Okay, so there are several dimensions, whether you can cover all the expressivity on a model, whether you can detect all type of faults, and when you create a formal verification tool, you have to decide which of these are going to be your strengths and which are going to be your weaknesses. So in this paper, what we have used is a specific approach to perform this formal verification, which is called constraint programming. Constraint programming is a declarative problem-solving methodology. In what you do is you express the problem in terms of a set of constraints that need to be satisfied. For example, a Sudoku problem might be a very simple example of a constraint problem, in which you have to fill in some gaps according to some constraints. We have used a specific variety of constraint problems called constraint satisfaction problems, in which the problem is decomposed in 3 dimensions. A set of variables that need to take values within a given domain, and a set of constraints that these values need to satisfy. And one specific, another trivial example of this would be the n-queens problem, in which you have to place queens in a chessboard without each threatening each other. This is a very example of a problem that can be decomposed in this way. The contribution of this paper has been using constraint satisfaction problem as the formal notation that we are using to verify models. Okay, we are using a specific constraint solver called Eclipse, which is very efficient and is able to perform this verification and to find errors efficiently. And specifically the contribution of this paper has been being able to encode the rich expressivity of the UML class diagrams into this formal notation. Regarding what are the advantages and disadvantages of this tool, as I have already said, the main advantage is regarding the expressivity of the models that this tool can analyze, the efficiency of the solver that we are using, and finally the type of feedback that we are producing. That is very useful to the designer. On the other hand, we are following what is called a bounded verification approach, so that the answer that we get is inconclusive, so that at some points we might get a I don't know answer from the tool. Okay, so regarding for further work, we are working precisely on how to improve the set of cases in which the designer gets a I don't know answer. So that would be all for my part, and thanks for your attention. This is some further information in case you want some pointers on how to continue on this area of research. Thank you.